All right, last time we started section 1.3, and in section 1.3 we had taken a look at evaluating limits analytically. And another word for analytically we talked about was the word algebraically. So it means there's going to be some sort of algebra involved, whether it's simply evaluating, plugging the number in, whether it's factoring, or the last thing that we had encountered right before we left was this one. Oops, where would it go? Did we do number 4? Did I skip it? I totally skipped it. Very interesting. I'll go back to it today. I'm sorry about that. Maybe I was just so excited about getting to number 5. This is the one that we did at the end, right? Rationalizing. Okay. So as we're taking a look at these for this section, those are the basic techniques that we're looking at, and we're about to encounter the trig. Let's go back and catch number 4. Since I skipped it, I apologize for that. Number 4 is quite a bit like number 3. If you take a look back up at number 3, what we did is we looked for whether or not I could just evaluate. That's always the first step. Can I just plug the number in? Because just because it looks like a rational function doesn't mean you can't, right? You might be able to. So we'll start with number 4 here, and it's x approaching 4. So if we attempt to put the number 4 in, and you have to put it on top and bottom to see if it will work. It's not just enough to say, is it going to make the denominator 0? You need to know both. So if you put it on the top and you put it on the bottom, what values do you get as you try to evaluate?
0 over 0.
Yeah, we do get 0 over 0. So when that happens, it's sort of just a note to us. That means that we've got some factoring that we will for sure be able to do. If it gets you 0 over 0, there's either factoring, or in this case over here when we got the 0 over 0 and we saw the radicals, we were rationalizing the numerator. So over here though, there's no radicals, so we are factoring. So this actually is sort of our note to ourselves, right, is that this is equal to this. I'll shift it to the side. So we're going to take the limit as x approaches 4, rewriting it every single time, and we're going to factor. So how will this numerator factor? Okay, x minus 4, and what was that? X minus 1. Okay, I think that's, yeah, sorry, I have a typo on my paper, but yeah, okay. How about the second one?
X plus 4, x plus 4, or x minus 4.
X minus 4 and?
X plus
2?
2.
2? Yeah, x plus 2. Okay, so brushing up on some factoring if you need to along the way. So these match right here. Yep. So we can reduce them. If we've got 0 over 0, which we did, I mean, we checked it. We know we have a 0 over 0. It will have something that can reduce. Whether it reduces from factoring or whether it reduces over here because we've done rationalizing, it will reduce. So if you're not getting something to reduce, double check your factoring. Make sure you didn't make a typo in the factoring, basically. All right, so yeah, it's going to work out that we've got this piece. So this next piece that I'm writing is sort of optional on the rewrite step. You don't have to write this out, but just for the sake of identifying what really remains, this is what remains. Okay? And so whether you write this step or whether you evaluate from this step, you're ready to put 4 back in and see if it will now work. Now, it's still possible you get a 0 somewhere, right? Like that could happen. But you at least stand a chance now at getting things to not be 0 over 0. So we're going to try. So when I put the 4 in now, what do I get? 3 over 6, which is 1/2. How could you check to make sure that's right with other techniques we've used? You could graph the function, and by that we mean the original function, right, Josh? Yeah, the very original function. You want to make sure that if you're trying to attempt to check your work, you check it from the beginning, not something you've already made some adjustments to along the way, because you might have made the adjustments that have the errors in them, right? Yeah, so you could check it with a graph, and if you're doing it with a graph, you're just trying to zoom in and trace to try to see if you're really close to 1/2. There's one more way we could check it. What could you do? With tables, right? That's called numerical. So you could just check it with tables by putting numbers in that are close to 1/2, like 0.49. It's very close to 1/2, right? 0.51, Or you could get even closer than that, 0.4999, 0.50001, those kinds of things. You put those into a table, same thing. Are you getting answers that are getting closer to 1/2? Yeah, then you can feel pretty confident that you've made the right pieces of decisions along the way.
Would you be evaluating the limits with numbers around 1/2 or numbers around 4?
I'm sorry, around 4. I apologize. I was not thinking about the right number. I was looking at this one. You were right, around 4. Yes, so you'd be approaching 4. You'd be doing numbers close to 4. Thanks for pointing that out. Yeah, sorry about that. All right, so I promised you that we were going to take a look at some trig. That's the time. So we have 6 trig functions. These should all look familiar. Sine, cosine, and tangent, and then secant, cosecant, and cotangent. And all of these are very much the same. They simply say that you can put the value in, just like with polynomials, just like with rational functions, just like with radicals. All the functions we've had up till now have this ability. It has to be a number that's in the domain. So there are some domain issues with trig functions. Not with every trig function, but with some of them. So I'll let you write those down, and then we'll keep talking about those domain issues. So graphs of sine and cosine are really nice. There are those wave ones, right? They just go up and down, they're smooth, they're continuous. There's no problems with sines and cosines and being able to just take the number and plug it in all the time. But all 4 of the others, tangent, secant, cotangent, and cosecant, all have domain issues. Thinking about the graphs, do you know what those domain issues look like on a graph? What's that? The limitations, we have a different word for it than that, but I think you're thinking the right thing.
Vertical line.
Vertical lines, they're called, oh, you guys are so close. They're called asymptotes. And everyone says, oh, right, that one, yeah, asymptotes. So they don't have to be, asymptotes don't have to be vertical lines, but they are on trig functions, on all 4 of those. So in the case of trig functions, each of those other 4 trig functions do have asymptotes. Those are vertical lines, in this case, that you get close to and you can't touch. So just as an example, we'll draw a tangent, or I'll sketch tangent out for a moment. So for the tangent graph itself, it looks something like this. You guys remember that? And it keeps repeating itself. And halfway in between these, and my device is probably going to try and connect these, so just recognize that it's not going to draw them. It's not too bad. So there's this vertical line right here that you get really close to on the top part and the bottom part here, but you don't touch. On tangent, that's at pi over 4. So we're trapped between negative pi over 4 and positive, pi over 2, sorry. We're trapped between negative pi over 2 and positive pi over 2. Secant, cosecant, and cotangent all have variations of that, either at pi half values or at whole pi values, depending on which one you're talking about. So in the cases that those are those values, obviously you can't just plug those numbers in. But everywhere else you can. So when it talks about up here in the description, and it says, let C be a real number in the domain, that's what it's talking about. You can't just pull an asymptote value in there and just think it's going to work. It's not going to work on those values, but all the other ones are good to go. There are 2 special trig limits that you need to be aware of, and we won't talk about how these are sort of proven right now. I can't even remember if they talk about them at this point in your book. However, they do talk more about these in a later calculus class where these are coming from. So these special trig functions are very interesting. As you write them down, I want you to think about what would happen on the first one and the second one, because they're both x approaches 0. What would happen if you put 0 in for x and just tried to evaluate it like we've said we can? Okay, so take a look at them. Don't say anything out loud. Just look at both of them and see in your mind, what happens if I try to just put 0 in for x? It's not going to work. So why is it not going to work? What are you going to get? If you try to put your calculator, it will give you a math error. It'll say something like domain error, actually. It's more than that, though. So domain error just means there's a 0 in the denominator, which certainly would happen on these. But what's going to happen in the numerator on these as well?
Also 0.
You're also going to get a 0. And we talked about the fact that if you get 0 over 0, that means something else is happening, right? There's some other way to deal with the situation, at least in this section as we're looking at it. This is the way to deal with these. So these two are very special trig limits. The sine of x over x as x approaches 0, not as x approaches anything, but just as x approaches 0 is 1. And the same thing for the other one. The 1 over cosine, I'm sorry, 1 minus cosine x over x as x approaches 0 also is going to be 0 in that case. Not 1, but it's going to be 0. It does have a limit. So keep those two in mind. Those are ones you're just going to need to memorize because they're unique, and they will show up. Obviously, for homeworks right now and WebAssign and so forth like that, you'll just have the paper with you. You could reference it. When we get to a quiz or when we get to a test, if it shows up on those, you need to make sure you've memorized those two trig function special limits, okay? So we're going to take a look at evaluating some trig limits. So most of the time, we're just going to try putting the numbers in, whatever the limit is. So in case of number 6, it's the number 2. In the case of number 7, it's 5 pi over 6. Another thing that you will want to make sure that you remember or print out and help yourself remember is the unit circle. Y'all know what I'm talking about? Okay. If you know how to use your calculator to try to manipulate and try and figure out what the unit circle should have given you, that's fine too. It doesn't matter to me. You've got a calculator to use. That's great. But you do need to find the exact value, at least for the things that you're turning in written work. WebAssign often won't accept decimal approximations either. So if your answer ends up being, for example, square root 2 over 2, and you get some decimal approximation for it, that's not going to be sufficient. Okay? So keep that in mind. Okay, so for most of the cases here on this, we're going to be plugging things in, just like we were with the algebra pieces. But there's also going to be times when we're going to factor, and there's going to be at least something showing up here where we're going to have to use that special trig limits that we just learned in the last slide. Okay? All right, so on the first one, can I put the number 2 in and it be okay? Yes, I can. So we're just going to do that. Whoops, let me use my black marker. So I can do sine of, this is pi times 2, right? And it's over 2, not the sine value over 2, but the angle measure. So these 2's cancel. So I really just have the sine of pi. Okay, so this is where that unit circle stuff comes in, or your calculator, if you can manipulate with it. This one's not bad with your calculator anyway. What is the sine of pi? Close. Or what did you say? Nope, not -1. It's 0. Cosine of pi is -1. Yep, that's the one you're thinking of. Yeah, this one's 0. So just as a reminder, real quick, we won't do this every time we talk about unit circle, but this is the first time. So on the unit circle, if you're at pi, you're over here. And the sine value is the y value. So we've got 0. It's cool? Okay. The next one's harder because it's not a whole pi. So we're going to attempt to do 5 pi over 6. This has to work because it's cosine. There's no values. The same thing for the first one. It had to work because over here, what we saw is that for sines and cosines, the domain is all real numbers, so we can put all real numbers in, and it will work. So when I put in 5 pi over 6 here, cosine of 5 pi over 6, let's start with, what quadrant is that in? Do y'all remember? It is. It's in the second quadrant. It's down here. It's the lowest. Let me go back to a solid line there. It's the lowest value, at least in terms of the unit circle values, that's still in quadrant 2, right? There's one there, there's one here, and there's one here. There's 3 of them in each quadrant. And this is the lowest one. That's what 5 pi over 6 is. So 5 pi over 6 is over here. That's kind of mushy, sorry. But imagine. So we're right here. So let's talk about the sine first. This is cosine as a function. So in quadrant 2, is cosine positive or is it negative? Do you remember? It's negative, right? It's x values. Cosines are x values. In quadrant 2, those x values are negative. So it's a good place to start. We have a negative value here. I was trying to get that other pen to change over. There we go. It's negative. And at each of the 5 pi over 6 and 2 pi over 3 values, so the one I marked and the one up here, you have the same xy coordinate pair as the other one, but flipped. So one of them is square root 3 over 2, and the other one is 1/2. Those are the values that show up at these two intervals. We just need to figure out the point where we're at. What is that x value? Is it the square root 3 over 2, or is it the 1/2? It is the square root of 3 over 2. And if you didn't just remember because you've memorized the unit circle or looked at it recently, how could you reason through that? There's a couple of ways.
It repeats, right?
It does repeat, but how could we decide if we don't remember which one it is or where it's repeating from? Do you know which one of these is bigger? Square root of 3 over 2 is bigger. How do you know?
Square root of 3 is bigger than 1.
Yeah, the square root of 3 is bigger than 1, right? Yeah, the square root of 3, of course, is bigger than 1 because the square root of 1 would be 1, right? So this is the bigger one. Can you tell at the 5 pi over 6 point where we are, is the x-coordinate the bigger one or is it the smaller one?
It's the bigger one, it's the more negative one.
Yeah, it's further to the left, right? It's bigger. So in our quadrant where we are right now, this location has a bigger x value than it does a y value. It's closer, to the left side, if you will, than it is to the top of the graph. It's got a bigger x value. So the x value over here is the bigger one. So therefore, since these are my two choices, it has to be the square root of 3 over 2. And again, the reason it's the x value I'm looking for is because I'm looking at cosine, and cosine is x, sine's y. So this is square root 3 over 2. There's another thing you could do. Grab your calculator for me if you have it. I'd like for you to just type in cosine of 5 pi over 6. Tell me what it gives you. It's going to give you an approximation of a decimal. I don't know of any calculators that put it in radical form, although if you find one, let me know. Does yours put it in radical form? What do you have? Oh, you've got a scientific one. Okay. So if you have a scientific one, that's great. So yours probably doesn't, because I recognize your calculator. What does yours say, Emily?
Negative 0.8660. 254.
8660. Let me pause too and say, if you don't already have your calculator in radians, it needs to be. So change your mode to radians if it's currently in degrees. Did I get four? Is that 4 decimals correct-ish? Okay. So this is the number that we get as an approximation. Type in your calculator square root of 3 over 2. What do you notice? It matches, except the sign's different, right? Because we didn't put the negative in with it. Yeah, but the value is the same, right? The numerical decimal expansion is the same. So that's another way you could check if you're at a point where you're like, I don't remember which one of those two it is. Your calculator can help you. It can't turn it back into a radical, but if you know the two choices, and these are the two choices, then you can figure out which one it should be. Is that good? Okay, so we're going to work on tricks along the way as I have the ability to sort of, do so. We'll mention those. Okay, these two are the easiest ones because they're the most direct. We simply took the value, we plugged it in, we had to do some trig, but from the calculus standpoint, there's not a lot of calculus here. Started out with limits, we turn it into an evaluation function. It's okay? All right, the next two don't work quite so friendly in the sense that you can't just plug it in. What happens if you try to put 0 in on number 8?
0 is 0.
You get 0 over 0. Now, there are two options when you get that to happen. One option is to look at special trig limits. That's what this one is. I'll just spoil the fun and tell you. That's what this one is. The other option is to look and see if there's any factoring from a trig standpoint that you can do. That's what we're going to do on number 9. Okay? So, how do you know? Well, if there's factoring from a trig standpoint, you usually have more than one trig function involved. That's one way you know. Do you see 2 trig functions involved on number 9? Yeah? You don't have 2 trig functions involved on number 8. So that's not sort of the inclination that we would go to. So what do we do on number 8 to make it look more like the functions we had seen as our special trig functions, our special limits of trig functions? Well, how is this problem different than the one that we saw when we did the special trig function limits, like that previous slide? It has a 5. Okay, so the first thing we need to do is we need to move that 5 to the front of the limit. Okay, we can do that. We had a property that said we can. In fact, I'm going to pull it up because I want you to know that they're coming into play yet again, even though we haven't sort of verbally mentioned it again today. Do you see this number 1, the scalar multiple? The 5 in the denominator is a 1/5 scalar multiple. And the first property here says I am able to pull the number 1/5 to the front of the limit. That's a property of limits that I have. So that's what we're going to do first, is we're going to pull that 1/5 to the front. So it's going to look like this. I have a 1/5 in front, and then I rewrite the pieces just like they were before. The limit as x goes to 0 of sine of x over x.
Does that make a difference if you put the 1/5 after the limit?
Say that again.
If you put the 1/5 after the limit, like
You could do it like this. Let me show you what I think that you're asking me. You could do it like this. That would work. But what we want is we want the limit to be self-contained and look identical to the one we had before, one way or another. So either at the very beginning, you could put it at the end, it wouldn't hurt anything. Just because we have it in the other form, I'll leave mine at the beginning, but if you want to put it at the end, I'm okay with that. So what is this piece equal to?
1.
It's 1. So once we have it in precisely, identically the form that it should be, then we can change it and we can say 1/5 stays, and I can replace that limit with the number 1, because that is a property that we have, and it's equal to 1/5. It is very tempting to simply jump from here to here. I promise you I will take points off if you do. Okay? You can't do that. You're going to show at least a portion of the pieces that are going on behind the scenes. That's what we're working on in this section. Okay? All right. The next one, number 9. So let me make mention of a resource that I don't think I've mentioned before, actually, but it's inside of our Canvas classroom. There is a trig identities sheet that is posted for you. There are not a lot of trig identities that you're going to need to know on a regular basis, but there are a few. One set of trig identities are the quotient identities. You should know that tangent is sine over cosine and that cotangent is cosine over sine. You need to know those functions, okay? Those are the quotient identities. The second one you need to do is the reciprocal identities. So reciprocal identities say that sine is 1 over cosecant, for example, and that cosecant is 1 over sine. All right, so there's 6 trig identities that are reciprocal identities. Those 6 you should know. And the last one, though it's not coming into play here, we won't need it for today necessarily, is the Pythagorean identities. So the Pythagorean identities, there's 3 of them. The one that's most commonly used, that you are most familiar with, is sine squared plus cosine squared equal 1. Okay? So if you don't have those memorized, or if they're just ones that you haven't seen in a while and you want a reminder, print that off from Canvas. Okay? Have that with you as you're working on your problems and so forth until they start to feel more familiar and you've got them down again. Okay? They are the most basic ones, and we will see them used over and over throughout the course. You'll need them. Okay? For this one, we see cosine. That's one of the ones that's pretty standard that we don't mess with. We just kind of leave it. And we see tangent. So tangent has 2 choices based on the descriptions that I've just given you of things I'm asking for. One is the reciprocal identity. I could change tangent into 1 over cotangent. But that doesn't collapse very nicely with the value in front of it, the cosine. So that's not the one I want to go with. The other trig identity that would be helpful or potentially helpful for tangent is the quotient identity. What does the quotient identity say that tangent is equal to? Actually, I'll write it down here. What was it? Sine over cosine. So this one's the one I'm going to work with. And the reason I want to work with this one is, do you notice how there's a cosine right here? And we have cosine in our equation itself, not equation, but our expression itself. That's why it's going to be helpful. Okay, so you're looking for things to sort of start matching up. So if you take a look then back up here, you can rewrite this. This is the limit as x goes to 0. I still have cosine of x. And now instead of tangent, I have sine x over cosine of x. And then I have x in the denominator, because that was there to begin with. So what do you suppose can happen based on the way you've seen this now? Yeah, the cosines cancel, you bet. And I'm left with the limit as x goes to 0 of sine x over x. But we know what that is. What does this equal to? It's 1. Now you could still confirm these, right? Like you could confirm this with a graph. You could confirm this with tables. There's nothing that's keeping you from doing that. None of that replaces the algebra work we're doing or the trig simplification that we're doing. It doesn't replace it. But at least it can confirm to you that you haven't made a mistake. You're getting the same answer in 2 different ways. Okay? Any questions on those? All right.